So a very good evening to all of you. Welcome to the final lecture of the STEMS 2022 qualifier camp that's being conducted in partnership with the Raising a Mathematician Foundation. So the final session will be by none other than Professor Murty of the Queen's University, Canada, where he is the Queen's Research Chair. Professor Murty is a leading figure in number theory. He received his PhD from MIT, where he was supervised by Professor Harold Stark. And he's particularly interested in modular forms, elliptic curves, sieve theory, and so on. He's a recipient of various awards, including the Coxeter James Prize, the Fellow of the Royal Society of Canada, the Fellow of the Fields Institute, the Indian National Science Academy, etc. And apart from mathematics, he also shares a very profound passion for philosophy in general and Indian philosophy in particular. So if you haven't seen his homepage already, you're definitely in for a treat. And he's the author of various books, including those in math and philosophy. And furthermore, he has a very deep connection with CMI in that he has mentored many of his students who either are or were in CMI. So for instance, Professor Purushottam Rath, Professor Anup Dikshit, Professor Jyotsna Shivaraman, Professor Siddhi Pathak, Dr. Abhishek Bharadwaj, etc. And today we'll set out on a journey titled The Art of Research. So a quick comment, please use the chat box for your questions, and without any further ado, over to you, Professor Ramurthy. Stage is yours.
Okay, well, thank you very much, all of you who have invited me to speak at your conference. So what I want to talk to you about is the art and science of research. Hopefully this will help. Okay. So firstly, are you seeing this window obstructing? Oh, it's disappearing. Okay, good. So first disclaimer is that the talk does not aim to give any recipe on how to do research. If there was such a recipe, then we can program computers to make discoveries, and that's not the case. However, there are some general principles that one can apply irrespective of any field. And in this talk, I'll try to outline these principles of research and give illustrations from science generally, and more specifically from mathematics. And the basic tools, of course, for research are
sorry to interrupt, so the window is still on the
and
screen.
Mind's movement. Is it still there? I don't understand how that, maybe I stop sharing and start sharing again.
Sure, yeah,
Try that, let's try that. Yeah, I'm gonna try and, it wasn't there before. How about now? Are you able to see
now
it?
It's great.
Okay. So basic tools are the mind and the mind's movement in time, called life. So these are what you need in order to do research. So the purpose of life. So let's have a look at that first. Let me get rid of this window here. Purpose of life. According to the Taittiriya Upanishad, life is meant for two activities only: study and teaching. Swajaya pravachanabhyam na pramaditavyam. That's the verse. Do not refrain from study and teaching. The human being is an organism that is ideal for this purpose. You see, we tend to think that we're hardwired, but we're not. We're in some sense soft-wired. The mind is very plastic. It's malleable, and it can be trained. In fact, the whole neural system can be trained, and that's what's going on. So, in other words, life is meant for education, and more importantly, perhaps self-education. A great sage once expressed this beautifully. He said, as long as I live, so long do I learn. So, and this is the reason that human beings have been endowed with this marvelous instrument called the mind. So the mind is our tool. And all of us are where we are today. You're where you are, and I'm where I am, I suppose, today because of our mental development. And so whatever we want to study, the tool is the mind. So the study of mathematics, is different from the study of anything else, such as other sciences like physics, chemistry. It seems to be both an art and a science, and no other subject seems to enjoy the status. So the study of mathematics requires a mind that is not only scientific, but also artistic. So we not only want to prove theorems, but we want beautiful theorems and beautiful proofs, whatever that may mean. We all know that beauty lies in the eye of the beholder. So part of our education is learning to see beauty. So let's look at the artistic side of research. Wonder if I can remove this. Are you seeing this window at the top by any chance?
No.
I'd like to remove it.
No, the entire screen is visible.
From the screen. Are you seeing that top window?
No.
Is it okay?
Yes, this is good. We can see your entire screen.
I mean, there's this kind of. Oh, you can see. Okay, all right. So on the one hand, we need to have a high order of logical thinking, which is essential in all of sciences. On the other hand, we need to have a high order of a sense of beauty or aesthetic delight. So this talk is about how to cultivate both of these qualities so that for the graduate student to do research, whatever that word may mean. So to make that whole process of research a little easier. So this is what I'm going to call the art and science of research. What are the principles, the ABC of research? So what are the essential qualities we need to bring in to our mathematical study? There are three. One is attention, and the Sanskrit word for attention is avadhanam. Second is beauty, which is Sanskrit word is anandam. And the third is classification, adhyayanam. So these are the three principles of research: attention, beauty, and classification. Avadhanam, anandam, and adhyayanam. These three qualities are not, of course, linearly organized, but rather should be developed simultaneously. And regarding the third quality, the student must get into the habit of making notes or having a notebook to systematically cultivate these three qualities. I emphasize this because we're now, we have entered this digital age, and unfortunately, I'm noticing many students are not in the habit of taking notes. Some students, in fact, come into my classes and just take pictures. So that is not the way to learn. I suggest strongly that even don't take notes into your notepad, rather take it on an ordinary pad, a regular pad with a pencil or a pen, and learn to organize your notes that way. So believe it or not, that seems to be a very important process of mathematical research. All of you, of course, have learned about the famous notebooks of Ramanujan, were discovered. Some of them have been discovered after his death. And you see through those notebooks how Ramanujan was struggling to come up with his theorems. So even such a great mind like Ramanujan had notebooks, so what to speak of us lesser mortals. So the preparation for discovery, the first step is to find some mathematical theorem that you find beautiful or remarkable. So if you don't find what you're studying beautiful, I would have to say, leave it immediately, because the only way you can make a mark in the study of anything is to find what you're studying beautiful. So you have to find that. Of course, it could be a little technical, but that's beside the point. The perception of beauty must come first. So that is, there it is on the mathematical landscape, like the Himalayan peak, and you gaze at it in wonder and awe of beauty. So you have this sense of beauty. And as you gaze at it, attention, how to explore it further. and you discover the steps, the classification to climb upwards, and slowly a theory starts to emerge. So this is basically the process of preparation for discovery. So let me now discuss the science of research. Now, research begins by asking good questions. The method of questioning is the way to gain knowledge in all philosophical and scientific traditions. But these can't be idle questions or speculations. They must be precise and have a singular goal of achieving greater understanding into the nature of things. Now, as this mental process, it's a mental process, it requires energy and stamina, that the instrument for research is your own mind. And so now we need to know how to use this mind in order to discover new things. And the process of this method of energizing the mind is brought about by churning the mind. Now, there's a famous story in the Puranas called Samudra manthan. You may all know it, where the Vishnu Purana, this remarkable story called Samudra manthan. The Devas and the Asuras wanted Amrutam. They wanted knowledge, and they realized that they have to churn the ocean, but they have to join forces. This is the interesting aspect of the myth.
There seems to be a network issue. So I think you've got muted also. Screen sharing has stopped. And we can't hear you.
You can't hear me. Can you hear me now?
It's good now, yes. But the window, the tiny window is back again in the middle of the screen.
Okay. Well, that's what, okay, I'll try to get out of this. So for every time I have a picture, I think is the problem. Okay. But after churning, after the churning gives rise to all sorts of jewels of knowledge. So how to churn the mind and how to ask questions is basically what I'm trying to say is the moral of that story. And so this is a nicer picture. I think these pictures are problematic to the transmission. Anyway, I'll present an eightfold way of asking good questions of essentially churning the mind. And the answers may depend on how you identify yourself. So here's an example. So supposing the question is, what is 2 plus 2? If you're an engineer, you'll take out a calculator and find the answer is 3.999. Depends on the accuracy of your calculator, of course. The physicist will run an experiment and finds that the answer is between 3.9 and 4.2. And so there's an experimental error. The mathematician says he doesn't know, but can show the answer exists. The philosopher asks for the meaning of the question. And the accountant asks, what would you like the answer to be? So it depends on who you are. So let me begin with a kind of first method of research called the survey method. The survey method consists of 2 steps. First is to gather facts, and the second is to organize them. Should I try to stop sharing and start this again? I mean, I think the pictures are the problem in this transmission.
Possibly.
Are you
maybe the small window disappeared.
Has it disappeared?
No, it's now there. So when you restart the screen sharing, it disappeared, but it's still there now.
Yes, so well, it keeps coming and going, doesn't it? Right?
Yes.
You didn't notice that?
Yes.
For me, it's coming and going. So let me just stop sharing and start sharing again. Okay. You can see it now.
Perfect. The window has disappeared. That's good.
Yeah. Okay. The survey method consists of two steps. First, organize facts, and first gather facts rather. Second is to organize them. The arrangement of ideas leads to knowledge and understanding. So what's missing is also revealed. So this is the survey method, the easiest method perhaps to do research. Superb example of the survey method is the discovery of the periodic table in chemistry. So I'm going to give you the story about that, the periodic table. Dmitry Mendeleev organized the existing knowledge of the chemical elements and was surprised to find a periodicity in their properties. So in the process of trying to write a student text in chemistry, Mendeleev decided to gather all the facts about the known elements and organize them according to their atomic weight. And the periodic table now sits as the presiding deity in all chemistry labs. So this is a remarkable school teacher. Essentially, Dmitry Mendeleev was a high school teacher who wanted to teach his students about the chemical elements and their properties. And he tried to organize them into groups. And so he found this periodic table, and then he discovered that there are missing elements, as it were. And each discovery of a missing element predicted by Mendeleev led to the award of a Nobel Prize in chemistry. It's an amazing story. The second method of discovery is patterns, and patterns lead to the question why, opening the door for the underlying theory that explains the patterns. So an example is this famous Michelson-Morley experiment, that the speed of light is constant independent of any relative motion of the observer. So these two cartoons or caricatures illustrate, I mean, unfortunately my animations are not working, but anyway, this particular Michelson-Morley experiment, frame, and in the second experiment, it's a moving frame. So if, as you know, if the whole thing is moving, the speed of light should be the stationary speed of light plus the moving speed. But Michelson-Morley found that this is not the case. Somehow speed of light is constant regardless of the frame, whether it's fixed or moving. That was made by Michelson-Morley, and that led to the discovery of theory of special relativity. The third method of discovery is by understanding conjectures. Michelson-Morley experiment could not be explained by Newtonian physics. So this led to the conjecture that there must be a larger theory that will explain the observation and fixed. And from this standpoint, the Michelson-Morley experiment is a contradiction. And the startling axiom then is that space and time are not absolutes. And they seem to conspire with each other to ensure the constancy of the speed of light, whether the observer is in a moving frame or a stationary frame. So this is basically the new physics that emerged out of the Michelson-Morley experiment. We'll return to this later. Now, here's an example in mathematics about, conjectures of Ramanujan. 1916, Ramanujan was studying the coefficients of a certain infinite product, and he observed some remarkable properties. This product is given by this infinite product, 1 minus q to the n to the power 24 times q. And when you expand it as a power series in q, you get these coefficients called tau n. And Ramanujan tabulated some of these values, and he noticed that the power series starts out q minus 24 q squared plus 252 q cubed, ... And then what he noticed was if you take the second coefficient and multiply by the third coefficient, you end up getting the sixth. If you take the second coefficient multiplied by the fifth coefficient, you get the 10th. So he started noticing multiplicative properties of these coefficients, and he made these conjectures that tau is multiplicative. Tau mn equals tau m times tau n, whenever m and n are relatively prime. And he also observed that tau satisfies a second order recurrence relation for prime powers. And the third conjecture was tau of p was always less than 2 times p to the 11 halves. So these are the 3 conjectures, famous conjectures that Ramanujan made in 1916. And these conjectures were kind of proved very quickly. First 2 were proved very quickly by Mordell in 1917. But the third one had to be proved using heavy-duty algebraic geometry, which was discovered only later in the 1970s. And so this is an important story of how conjectures can stimulate a whole century of discovery. So these conjectures led to the development of the theory of modular forms. So most of you may know, some of you may know about the theory of modular forms as being very important, but these conjectures were important for that. Another way of making discoveries is by a method called reinterpretation. So what does this do? This method of research examines traditional concepts and tries to look at them in a new light. So we're going to come back to that Michelson-Morley business. So such a method does not negate past understanding, but expands it and sees it as a special case of a larger phenomenon. The Michelson-Morley experiment forced physicists to re-examine Newtonian physics and to question its fundamental axioms. First and foremost were our notions of space and time. So the special theory of relativity, as most of you know, was discovered by Einstein. Einstein's special theory of relativity postulates that time dilates and space contracts in order to make sure that the speed of light is constant, irrespective of the frame of observation. So this was a really remarkably new idea in the theory of relativity. His theory reinterprets space and time. They're not absolutes, but they are, and nor are they independent, but they're interdependent. So they're interdependent, and now we don't speak of space and time, we speak of space-time with a hyphen, in the sense that they are intertwined. And in Einstein's theory, gravity is not a force, but rather a curvature of space. So Einstein's theory led to a new view of gravity, not as a force, but as a curvature of space. So it's like some picture like this, where you have a like kind of trampoline is the space, and the planet is sitting in the trampoline, and it curves the space. And for example, the sun curves the space, and that planets move in these curved grooves, as it were. And this particular new view of gravitational fields as being curvatures of space led to the remarkable idea that light bends due to gravitational force. And this is a prediction that comes out of the theory of relativity and was actually corroborated in this famous experiment where this planet that you see should not be visible, but was visible simply because the light coming from that star was bent due to the gravitational field of the sun. And this was first noticed by Chandrasekhar. And Chandrasekhar also noticed that stars can collapse. And if the star is really, really massive, the curvature of space is so much that it's almost like a hole in space. And this is the theory of black holes. So the birth and death of stars in 1938, Subramanian and Chandrasekhar showed that this view of gravity allows for the existence of black holes. Now, he wasn't offered the Nobel Prize at that time because there was no experimental verification. That was done in the 1970s, I believe, by this guy called Fowler. And Chandrasekhar and Fowler were then given the joint Nobel Prize in the 1980s. But this was already seen as a consequence in the work of Chandrasekhar. Now, another way of, in the mathematical context, how to understand reinterpretation, I want to reinterpret unique factorization. So we may think we know what unique factorization is, but here's a little cartoon that shows that what reinterpretation is all about. So we always talk about unanswered questions in research, but in some sense, research can also begin with questioning old answers, especially when it comes to religion and philosophy, I suppose. All these answers that have been given in various texts can easily be questioned. And when you question those, not in a callous and disrespectful way, but it turns out you will get new knowledge. So let me kind of illustrate this. The idea is to try to see familiar things in a new light. So most of our difficulties in research is that we are too dull. We dismiss things. We mistake the word for understanding. So, oh, what is yoga? Oh, I know what yoga is, and end of story. So you never investigate. You think you know, but you don't know. So you're kind of clouded by your own opinion. You think you know algebraic geometry. You think you know number theory, but then you don't. So most of our difficulties come with passing out opinions on things we actually don't know anything about. And so we never stop to question. So being a philosopher, being a scientist, being a mathematician means to stop yourself and ask yourself, do you really know? Or is this an opinion that you have? So better not to make pronouncements on things and try to see familiar things, don't dismiss things, but see familiar things in a new light. So let's take a well-known theorem and see how that applies. Every natural number can be written as a product of prime numbers uniquely. Now, there's a new way of looking at it, and there are probably more ways to look at it we have not yet discovered. But let's just see how to reform. Is there a reformulation that leads us to a higher understanding? So Euler did this exercise. He discovered that unique factorization theorem can be written analytically. So here's a picture of Euler. And he noticed that if you look at this series, zeta of S, which is this summation of the reciprocals of the S powers of all the natural numbers, then you can rewrite unique factorization as a statement that says that that infinite series is really a product over primes of this geometric series 1 plus 1 over p to the s plus 1 over p to the 2s dot dot dot. So you have an infinite series is equal to an infinite product over primes. And this is the way Euler thought of unique factorization. And one of his remarkable contributions is that he comes up with a new proof of the infinitude of primes, which you, of course, probably know from Euclid's Elements. Euclid gave a proof of the infinitude of primes, but Euler had this more seemingly complicated proof, which says that because the harmonic series diverges, there have to be infinitely many primes. So this reformulation opens the door to study prime numbers by analytic methods. And it turns out that even though this complicated proof that Euler had given for the infinitude of primes, via this reinterpretation of unique factorization, it turns out that this method of proving infinitude of primes generalizes to arithmetic progressions and other more exotic settings. Now we could try to reinterpret Ramanujan's conjectures. Remember those conjectures? So you have this multiplicativity of the tau function. That can be reinterpreted also as a statement that this series summation tau n over n to the s equals product over primes being given by tau of p over p to the s times p to the 11 over p to the 2s. And the first two of Ramanujan conjectures can then be reformulated as saying that these two are equal. So that's another way of reformulating Ramanujan's conjectures. And they were proved by Mordell in 1917, but really this interpretation and the profound theory behind Ramanujan's conjectures was only unraveled by Erich Hecke in 1936, gave the theoretical basis for Ramanujan's discoveries. And finally, the third conjecture about the bound on tau of p was solved by Deligne in 1974 using algebraic geometry, and Deligne won the Fields Medal for this work. A fifth method of generating research questions is called the method of analogy. Method of analogy detects similarities between two seemingly separate ideas and tries to find an underlying theme for which to view both. For instance, we see some similarities now between Euler's product zeta s and Ramanujan's product. So now that we have reinterpreted unique factorization on the one hand as this zeta function being equal to an infinite product over primes, and that Ramanujan's conjectures being also in terms of an infinite series is equal to an infinite product, the question arises, is there some sort of underlying theory? There's an analogy. So is there an underlying theory? So we have these two objects, these two what are called Dirichlet series, looking similar. And they, on one hand, this is an infinite product. On the other hand, this is an infinite product. So both are infinite products. And so the question is there a larger theory of things? And the development of this analogy is what's called the Langland's program. So some of you may have heard of this Langland's program. It connects several branches of mathematics. One is number theory, another is representation theory, another is algebraic geometry. So wonderful connections between all these branches of mathematics. A sixth method of generating questions, good questions in research is method of transfer. So the idea here is to take one idea in one field and transport it into another field. So in one aspect, it is to look for applications, whether they're in the theoretical realm or in the technological realm. An example is provided by coding theory. In the 1950s, a fundamental problem was how to signal, how to deal with errors in the transmission of a signal. See, for example, when you send out a satellite out into space, let's say, and it's supposed to take pictures of Jupiter and send it back to the Earth. What happens is that the signal will meet with the asteroid belt and probably get changed. So if it's trying to send a picture to you, of course, the picture is digitized, and suppose the color red is designated as 1, and the color blue is designated as 2, and if it tries to send you the number 1 and the number 2, they might get, 1 can get changed to 2, and 2 can get changed to 1, so the whole thing could be a complete mess. So Shannon in the 1950s came up with a really remarkable idea of don't use number 1, number 2, use the number 100 and number 200. So if you use the number 100, that's three digits that you have to transmit. And so even if it was changed in the course of running to the asteroid belt, let's say 100 got changed to 120, by the time it got to Earth, you will know that there was 100, so it must have been 100. And so there's a way to kind of correct the error. These are called error correcting codes. So this really is basically the idea behind cable television, behind data compression that you're using, right? Compact discs, DVDs, and data, these memory sticks that you carry. All these things are based on this simple principle of coding theorem, how to compress and correct the errors. So this was first addressed by Claude Shannon in a fundamental 1948 paper called the Mathematical Theory of Communication. So here's a remarkable idea. It's not there's no new math, but it was taking an idea from one field, basically the theory of finite fields, and then moving it into this realm of applications. So there are these Reed-Solomon cones. If the data is, so now you can get more sophisticated things. Data is to be transmitted by a sequence A of 0, A of 1, up to A of n minus 1, with A of I lying in a finite field, K of P elements. Then an idea of Reed and Solomon is to create the polynomial A of 0 plus A1x plus dot 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 A of m minus 1x to the m minus 1. And then if G is a generator of K, then we transmit f of G squared, f of G in the end with n larger than the degree of the polynomial. And as you know, if you have the values of a polynomial for more than its degree, then you've got the polynomial, and therefore you have all these coefficients. So famous theorem of Lagrange tells us that a polynomial of degree m can have at most m roots in a finite field. And this enables us to retrieve the original message accurately. So this is another way of using a familiar theorem, transferring the theorem from pure mathematics, algebra, theory of finite fields in this case, to the world of technology. So the idea is now to use, this now is used in satellite transmission, cable television, I told you already, and all forms of digital media. It is the essential idea behind all forms of data compression. Just imagine this digital age that we're living in right now. You're literally carrying libraries in your pocket. And the reason you're doing that is because the theory of finite fields. A seventh method of discovery is what's called the method of induction. Induction is really a method of generalized instance of induction is, of course, mathematical induction. And this is an example discovered by Aryabhata in 500 CE, India. One has, for example, 1 cubed plus 2 cubed equals 9. 1 plus 8 plus 27 is 36. It turns out to be another square. And you're tempted to guess that 1 cubed plus 2 cubed plus n cubed is equal to n times n plus 1 over 2 whole squared. And indeed, this is true, and all of you can probably prove that just using simple induction. This was done by Aryabhata way back when. A more interesting illustration of this principle in induction is given by L-functions that I've been alluding to kind of in the previous slides. There's a hierarchy of L-functions. So what Euler, Riemann, and Ramanujan discovered were special cases of a hierarchy of L-functions that we now know exist corresponding to GLN. And this is the famous Langland's program, and the roots go back to Hecke's generalization of Ramanujan's work, representation theory of Harishchandra. So these are Hecke and Harishchandra and Robert Langland. So we have a kind of a progression of ideas, starting with very classical number theory, and all of a sudden the work of Harishchandra, representation theory of p-adic groups, and somehow Langland's putting all this together and saying that they're all connected, and we have this remarkable Langland's program. Finally, I want to talk about the so-called converse method. So the converse method of generating good questions is simply whenever you see a proposition that says A implies B, you can ask, does B imply A? And such a question often leads to profound discoveries. An example is provided by the discovery of electromagnetism. Now, currents create magnetic fields, so that was already kind of known. So the converse question is, does a magnetic field create an electric current? And this question was first asked by Michael Faraday, and he ran an experiment to show that indeed it's the case, and this led to the theory of electromagnetism. So that's an example of the converse method. So let me try to summarize what I have said so far. The art of research is really about the art of asking good questions. And the art of asking good questions has a lot to do with the development of attention, an appreciation of beauty, anandam, and the ability to organize thoughts, classification. So A, B, C. A is attention, B is the sense of beauty, and C is classification. And then if you want to ask good questions, I've offered you the eightfold path, eightfold way of asking questions, 8 methods. So what were they? They were survey. So if you want to study something, you survey, organize ideas. So don't think that, right, for example, Dmitry Mendeleev was writing a high school textbook. And in the course of writing this textbook, he was organizing ideas. In the course of organizing ideas, new ideas come and new methods of research open up. I remember running into several professors at the Tata Institute ages ago who used to frown upon people writing books, saying writing books is for old people or something like that. I think that's a misplaced notion of the idea of research. When you write a book, especially at an advanced level or a graduate level, you organize this jungle of information. You know, you can always point the student to the library and say, go read. That's a very cruel way of teaching. Rather, the best way of teaching is to take the highlights and in a 12-week course or something, give the essential ideas, and that takes work on the part of the teacher to organize these ideas and put them into some sort of coherent narrative. The narrative should also be interesting and engaging. the teacher must also inspire by amplifying the aspects of beauty in the knowledge that is being surveyed. So survey is the method of the easiest, perhaps, method of generating questions. The next method is, of course, observations. You make very careful observations. Ramanujan, for example, observed very carefully the infinite products that he generated had some remarkable properties, and that led to the theory of modular forms. So it's careful observations. I gave you the example of Michelson-Morley experiment, which led to the theory of relativity. So these are not jokes. Careful observations, not to dismiss things, but to carefully look at things. We really don't know many things, actually. We think we know, but we really don't. And not to come to judgment about ourselves or about others, or about fields for that matter. Next, by making observations, you see patterns. And these patterns, you may not be able to prove that these patterns are legitimate theorems. You make conjectures, you'll test these conjectures. So in that context, conjectures are a natural outgrowth of any patterns. For example, the famous Fermat's last theorem, Fermat noticed that you could take two squares and add them up, 3 squared and 4 squared, get 5 squared. But he asked the question whether the same thing works for cubes, and he noticed it didn't. And he asked for 4th powers and probably had a proof for that, and probably mistook that proof generalizes and made this famous assertion that for every n, there are 2 nth powers do not add up to another nth power. And that's, of course, most of you know, is the famous Fermat's last theorem. So that's a famous conjecture that inspired about 300 years of work in number theory. The 4th method of generating questions is by this method of reinterpretation. So you take something that you actually know, and you don't dismiss it so easily, and you reinterpret it. Einstein reinterpreted the gravitational force of Isaac Newton's theory as a curvature of space. He was forced to re-examine notions about space and time as not being absolutes, but interdependent, and somehow them conspiring to keep the speed of light constant. So there was a new revolutionary idea. It had to do with reinterpreting notions like space and time. The 5th of things happening in one field, and we try to see if the same thing happens in another direction. And a 6th method of generating good questions is by the method of transfer. You take an idea from one area of mathematics and you transfer it, like Shannon's theory of communication. So he took the ideas from the theory of finite fields and tried to use that to build what are called these error correcting codes. Another method of induction. So you see a pattern, like Aryabhatta noticing the patterns between sums of cubes being equal to sum of the first natural numbers to the 4th power. So that's an amazing observation. And you observe, and then you induct, and by method of induction, you can generate new questions and new theories. And finally, the converse methods. Every time you prove a theorem that A implies B, you can always ask, does B imply A? And this is a very natural question to ask. And when you do that, ask that question in all seriousness, you end up discovering new things. Now, if you felt that you should have been taking notes, I can give you one slide, and through that you will be able to realize that there was really no need for you to take notes, because the essential ideas of this lecture are summarized by the mnemonic, Socratic. So with this mnemonic device, which is essentially a mental memory device, you immediately can recite the essential principles of this talk without having taken notes. You see how the use of the mind comes into the picture of understanding and learning. So let us all churn our own minds and journey inward And there we will find gems of great discoveries. So thank you for your attention.
Thank you, Professor. Thank you for this beautiful and wonderful talk. I mean, like how you started with examples from various fields, not only maths, like, but from physics and chemistry, and how you related everything so simply and so nicely. And it was really wonderful. I mean, I don't have any words to express how I'm feeling after this talk. And thank you for your mnemonic. It will definitely help all of us and also our participants in their future research career. So I'm pretty sure people must be wondering a lot of things right now. So if you have any questions, you can definitely ask now. If you have any questions. So there was one question in the chat that when you said about the Ramanujan conjecturing about the tau function. So one question was, how did he come up with the bound of 2p power 11 by 2? Like, how can someone think of such a bound?
Yeah, that's a good question. If you remember infinite product, if you take his first two conjectures, those first two conjectures can be rewritten as saying that Dirichlet series is equal to that infinite product. And in order for that denominator not to have any singularities, you had to have that inequality. That was basically the motivation. So if you look at that quadratic, I believe that the corresponding quadratic turns out to be 1 minus tau of p x plus p to the 11 x squared. That's what basically, and x you put p to the minus s. So if you look at that Euler factor, there's a quadratic polynomial that's been evaluated at p to the minus s, and that polynomial turns out to be 1 minus tau of p x plus p to the 11 x squared. So another way of thinking of it is x squared minus tau of px plus p to the 11. If you flip it around. So x squared minus tau of px plus p to the 11 is a quadratic polynomial, and the discriminant of that polynomial is, classical high school formula, b squared minus 4ac. What is it? B squared is tau of p squared minus 4 times p to the 11. And you have to have that to be negative. If it was positive, you'll have real roots and you'll have a singularity there. If it's negative, you won't have any singularities, at least on the real line. And this was one of his motivations, and that turns out to be the correct insight in Hecke's theory as well. So that's how he was led to that formula, inequality.
Great.
Thank you. It's an amazing idea. Yeah, thank you for the question.
So if you have any questions, also you can write to us later on our email ID, and we will get them answered. So if there are no other questions, then I think we can conclude the session. So join me together to thank Professor Ramurthy for his such a beautiful talk, and I'm pretty sure that you all will follow these ideas and try to implement at various places. And so thank you, Professor, for your final talk. So Pranav, I think, okay, you have one question, so maybe we can take that question. Pranav, you can unmute yourself.
Yeah. So like sometimes when I'm doing a question or something, I think of a question, which is like not a Olympiad or math question, but like something of a sort of which you can think over for a long time. So basically kind of that four coloring theorem, there was one, right? So something related to that. So do you think it's good to like spend some time on it in the daytime, even you are in high school, or you can save it for later times when you have more time and you're more into the research things?
Yeah, no, that's an excellent question. So as you know, I think the four color conjecture has been solved, but it has not been solved. It has not been solved from the aesthetic perspective. It has been solved from, using computers. So it doesn't meet the criterion of the beauty criterion that I kind of gave in my talk. It fails in that sense. And from Europe, yeah, absolutely. I think that there is some merit in thinking about the four, now that we know that four colors work. I think there is some merit in trying to think of some method of solving the four color conjecture more beautifully using theoretical understanding rather than computer calculations. I mean, that is a gap in that, and I think that is a good problem to work on. If you know, there's a famous theorem of Haywood, who kind of connected this coloring questions to algebraic topology, basically the genus of the Riemann surface. So here, when we're talking about maps, we're talking about maps on the sphere. But if you were looking at maps on the donut, if you had a donut and you asked the torus, the torus, using the word donut so that people can understand more about the torus, basically, then it turns out that there's a formula that he came up with, which is the analog of the four color thing for any Riemann surface of genus G. And he proved, as long as the genus is at least one, he proved the analog of the four color problem for those things. The problem is we want it for genus 0, not genus. He got it for genus 1 and higher. So he obviously came up with a conceptual topological understanding of the problem. The people that actually solved it using computers did it using graph theory and many reductions in graph theory. So, and it's also interesting, but I don't think there's a marriage between the two ideas. It might be worth looking at from that conceptual perspective. Actually, I have a paper that I wrote when I was a graduate student with Giancarlo Rota. And our main theorem in that paper is to interpret the four color conjecture and show its analogy to the Riemann hypothesis. Not that it's equivalent to the Riemann hypothesis about theory of prime number, but it actually has to do with zeros of certain zeta functions. And I believe nobody has picked that up as a kind of a viable method of research. Hopefully somebody will, but it seems to me we are looking for a conceptual approach to trying to understand the four color theorem. It should be visible at a glance. And the person who came closest to giving us such a visual, instantaneous understanding of the four color theorem was Haywood, because he came up with a formula. If the genus is G, he came up with the minimal number of colors needed as a function of G. But his theorem applies only for G is at least 1. When you put G equals 0 in his formula, you actually get 4. so you see, so it's so nice, it works, but it's not valid so there must be something missing between these two. So in that sense, I think it can be a productive line of research, but at the same time, you shouldn't get fixated or obsessed with a problem, because when you get obsessed with a problem, that's what Indian philosophy will call attachment. And attachment can lead to self-destruction. And the reason for that is because each problem has a certain historical element attached to it. Certain problems could be unsolvable. Certain problems could be such that the time is not right. You don't know. So in some sense, you have to feel your way through. There, as I said at the very beginning of my talk, There is no recipe that I can give you, but I can give you some guiding principles. And certainly if you're interested in certain topics, you should pursue them and you should go with a passion. But at the same time, you should maybe work on several other problems at the same time so that you see if we're making progress in one, you can at least push forward in that direction rather than investing all your money on one problem and being obsessed and becoming a nervous wreck also in the process. So we don't want to go there. Yeah. Does that help?
Yes, sir. Thanks a lot for the answer.
Thank you, Professor. Are there any other questions? I don't think. Yeah, Anirudh, you can.
There's no other questions. So if you have any questions, do feel free to write to us. And I'm certain that Professor Murty will be able to answer them. So thanks again very much for the lecture. It was extremely inspiring, and there was a lot to take away from it. Yet again, so this pulls curtains on the qualifier camp. So we hope that this camp has been a great learning experience to all of you. And we certainly hope to see you in the final camp, which is in the second week of February. But before that, best wishes for the final exam, which is in about 2 weeks from now. And so here's Amik Raj Behra, my co-host, and I, Anirudhan, temporarily signing off until the final camp. So thanks very much for putting with us throughout and attending the lectures, asking questions, and it was all very engaging. So once again, thank you very much, Professor Ramurthy, for this wonderful finish.
Okay.
Thank you.
Happy New Year to everybody. Happy New Year. Yeah.
Happy New Year.
Happy
Thank you, sir.
Yeah. Bye. Yeah. Okay.
Bye.
Thanks.
Have a good day.
Yeah.